Hi friends, here we have antiderivatives. The following theorem gives a necessary and sufficient condition for the integral to be independent of path of integration and for an integral around a closed path has value 0. We recall that contour is a piecewise smooth arc. First we have a definition of antiderivative. A function f is called an antiderivative of a function f defined on a domain D if f dash z is equal to f of z for all z in the domain. For example, the function fz is equal to 1 by 4 z raised to 4 is an antiderivative of what fz is equal to z cube on the entire complex plane, because for each complex number z, f dash z is equal to d by dz of 1 by 4 z raised to 4, and this is equal to z cube, which is our f of z. However, fz is equal to 1 by 4 z raised to 4 is not the only antiderivative of f on this interval. If we add any constant c to 1 by 4 z raised to 4, then the function g z is equal to 1 by 4 z raised to 4 plus c is also an antiderivative of f, since g dash z is equal to d by dz of 1 by 4 z raised to 4 plus c is equal to z cube plus 0, which is again our f of z. Next, we have a theorem. Suppose that a function f is continuous on a domain D. If any one of the following statement is true, then so are the others. The first one is, that is statement A. It says that f has an antiderivative capital F in D. Second one says that the integral of fz along contours lying entirely in D and extending from any fixed point z1 to any fixed point z2 all have the same value, namely integral z1 to z2 fz dz is equal to, which is equal to capital Fz over the limits z1 z2. This can be write as f of z2 minus f of z1, where fz is the antiderivative in statement A. Next statement says that the integrals of fz around closed contours lying entirely in D all have value 0. The theorem above does not claim that any of the given statement A to C is true for a given function f and a given domain D. It tells us only that all of them are true or that none of them is true. Now move on to the proof. We first prove that A implies B, that is the statement A implies statement B. Let f be a continuous function which has an antiderivative capital F in D, that is f dash z is equal to f of z, for z belongs to our domain D. Let C be any contour lying entirely in D joining Z1 and Z2. Now case 1, first case. Here our C is a smooth arc. Let C be a smooth arc with parametric representation. Z is equal to Z of t, where A less than or equal to t less than or equal to b, such that Z of A is equal to Z1 and Z of B is equal to Z2. Then integral over C f z dz is equal to integral over limits a to b f of z of t z dash of t dt. Equation number 1. Now d by dt of f of z of t is equal to, that is d by dt of f of z of t. This we can write as f dash of z of t into z dash of t. This is equal to, this we can write as f of z of t into z dash of t, small f of small f, f of z of t into z dash of t. Hence, 1 becomes, our first equation becomes integral over C f z dz is equal to this we can write as integral over a to b d by dt of what, f of z of t. Here this is f of z of t, integral a to b d by dt of f of z of t dt. This is again, this we can write as, this is equal to f of z of t over the limits a to b by using a theorem in the chapter definite integral. I think it is theorem number 7. This, on substituting value, we can write it as f of z of b, that is the upper limit, minus f of z of a. F of z of, here we have one more bracket, f of z of p minus f of z of a, or it is equal to what, f of z2 minus f of z1. This value is independent of the contour C as long as C lies entirely in D. Next case where C is piecewise smooth. Case 2, C is piecewise smooth. In this case, C consisting of a finite number of smooth arcs Ck, where k varies from 1 to n minus 1, joined end to end, where each Ck is a smooth arc extending from point Zk dash to Zk plus 1 dash, and Z1 dash is equal to Z1 and Zn dash is equal to Z2. Then from case 1, it follows that for each k is equal to 1 to etc. up to n minus 1, we have integral over Ck fz dz is equal to f of Zk plus 1 dash minus f of Zk dash. Hence, integral over C fz dz is equal to, that is integral over C fz dz. We can write it as integral over C1 fz dz plus integral over C2 fz dz plus etc. plus integral over C n minus 1 fz dz, which is equal to, it is up to integral C n minus 1 fz dz, which is again equal to f of z 2 dash minus f z 2 dash minus f z 1 dash plus again f z 3 dash minus f z 2 dash plus etc. plus what f z n dash minus f z n minus 1 dash. It extend up to f z n dash minus f z n minus 1 dash, which is equal to f of z n dash minus f of z n 1 dash, z 1 dash, which is equal to, last we have what remains, f of z 2 minus f of z 1, which is also independent of the contour C. Here completes the proof of A implies B. Next we have B implies C. Now let us assume that integrals of f z along contours lying entirely in D and extending from any fixed point z1 to any fixed point z2 all have the same value. Let C be any closed contour lying entirely in D. Let Z1 and Z2 be any two points on C. Also let C1 and C2 be two paths both with initial point Z1 and final point Z2. That is, it is just like this. C1, C2, this is our Z2, this is the initial point Z1, this is the terminal point Z2, and C is equal to C1 minus C2. From B, it follows that integral over C1 fz dz is equal to integral over C2 fz dz. Hence, we can say integral over C fz dz is equal to integral over C1 fz dz plus integral over minus C2 fz dz by the theorem in the previous session, which we can write as integral over C1 fz dz minus integral over C2 fz dz, that we know from previous sessions. Next we have C implies A. Now, let us assume that the integrals of fz around closed contour lying entirely in D all have the value 0. Let Z1 and Z2 be any two points in D and let C1 and C2 denote any two contours lying in D from the point Z1 to Z2. So, let C is equal to C1 minus C2. Then C is a closed contour, it need not be simple, lying entirely in D. Then by hypothesis C, we have integral over C fz dz is equal to 0. That is, integral over C means C1 minus C2 fz dz is equal to 0. This we know, integral over C1 minus C2 can be written as integral over C1 fz dz minus integral over C2 fz dz, which is equal to 0. That is, integral over C1 fz dz is equal to integral over C2 fz dz. Hence, integration in D depends only on endpoints and is independent of path. Let Z not be any fixed point in D. Define fz is equal to, we can define fz is equal to integral over Z0 to Z f of s ds for all z belongs to D. Clearly, f is a well defined function on D. Now, let z plus delta z be any point distinct from z and lying in some neighborhood of z, that is, it is sufficiently small to be obtained in D. Then f of z plus delta z minus f z is equal to this we can write as integral z naught to z plus delta z f of s ds minus integral z naught to z f of s ds. This we can write as, which is equal to integral, the lower limit is from z up to what, z plus delta z f s ds. Equation number 2. We know that if C is any arbitrary contour from a fixed point z1 to z2, then integral over C dz is equal to z2 minus z1. Hence, integral over z to z plus delta z ds is nothing but what, z plus delta z minus z, which is equal to delta z, and also f z is equal to f z is equal to 1 by delta z integral z to z plus delta z f z ds. Hence, from equation number 2, we obtain f of z plus delta z minus f of z divided by delta z minus f of z is equal to, here we have small f of z minus f of z, which is equal to 1 by delta z integral z to z plus delta z what, f of s ds. That is, it is equal to 1 by delta z integral z to delta z integral z to z plus delta z f of s minus f of z ds. That is our equation number 3, which is equal to 1 by delta z integral z to z plus delta z. In the integral we have f of s minus f of z ds. This is our equation number 3. Since f is continuous at the point z corresponding to any epsilon greater than 0, there exists a positive number delta such that mod fs minus fz is less than epsilon whenever s minus z is less than delta. Hence, if z plus delta z is close enough to z, so that mod delta z is less than delta, then from 3 we get from this equation, third equation, we can write modulus of f of z plus delta z minus f of z by delta z minus f of z, this is less than or equal to 1 by mod delta z integral z to z plus delta z modulus of f of s minus f of z dz. This we can write, which is strictly less than 1 by mod delta z into epsilon into mod delta z, which is again equal to what, epsilon. Hence, limit delta z tending to 0, f of z plus delta z minus f of z by delta z is equal to f of z, and therefore f dash z is equal to f of z for every z in the domain D. That is, f has an antiderivative capital F in D. Next, we will move on to evaluation of line integral second type. First example is evaluate integral I to 1 plus 4I z square dz. Here, taking fz is equal to z square, our fz is equal to z square. We have capital Fz is equal to integral fz dz, which is equal to integral z square dz, that is z cube by 3 plus c. So, our capital Fz is z cube plus c, z cube by 3 plus c. As f is an antiderivative of f by theorem 1, integral I to 1 plus 4I z square dz can be written as, which is equal to integral I to 1 plus 4I fz dz. This is f of upper limit 1 plus 4I minus f of I. That is, our f of z is z cube by 3. So, this is f of 1 plus 4I. So, this can be written as 1 by 3 into 1 plus 4I whole cube minus I cube. I am taking 1 by 3 outside, 1 plus 4I whole cube minus I cube. On simplification, this is equal to 47 minus 47 by 3 minus 17I. On simplification, we get it is minus 47 by 3 minus 17I. Next example is, next is integrate from I to pi by 2. It is from I to pi by 2 cos z dz. We have to evaluate integral I to pi by 2 cos z dz is equal to sin z over the limits I to pi by 2. This is simple. That is, sin z over the limits, we have to apply the upper limit pi by 2 and the lower limit I. This is equal to what? 1 minus I into sin h1. That is, since circular function sin yi and hyperbolic functions sin hy are related by sin yi is equal to I sin hy. So, we have it is 1 minus I sin h1. Next example, integral 0 to 1 plus I, 0 to 1 plus I z square dz. It is simple, it is z cube by 3 over the limits 0 to 1 plus I. On simplification, it is equal to 2 by 3 into minus 1 plus I. On applying the upper limit and lower limit, we get it is 2 by 3 into minus 1 plus I. Next example, it is integral over minus 2I to 2I. Minus 2I to 2I, here it is dz by 2. It is nothing but integral of dz by 2 is, it is a log z over the limits minus 2I and 2I. We have to apply to upper limit 2I and lower limit minus 2I to the value set. So, it becomes log 2I minus log of minus 2I, which is equal to pi I. That is log 2I minus log of minus 2I. So, the answer is pi I. Next, we have to evaluate integral over c z square dz, where the c is any contour from z is equal to 0 to z is equal to 1 plus I. That is, z varies from z is equal to 0 to 1 plus I. Here fz is equal to z square. Fz is equal to z square is continuous everywhere, and since d by dz of z cube by 3 is equal to z cube, fz has an antiderivative. Fz is equal to z cube by 3 for every complex number set. Hence, by theorem 1, integral of fz along C, where C is any contour joining 0 to 1 plus I, depends only on the endpoints 0 and 1 plus I, and integral over C z square dz is equal to, since it depends only on endpoints, we can write it is equal to integral 0 to 1 plus I. These are the limits 0 to 1 plus I fz dz, which is equal to f of upper limit 1 plus I minus f of 0. On substituting, we have it is 1 plus I whole cube by 3 minus 0 by 3, which is equal to 2 by 3 into minus 1 plus I. On simplification, we get it is 2 by 3 into minus 1 plus I. Next example, it is to evaluate integral over C dz by z square, where C is a positively oriented circle. That is, z is equal to 2 e raised to I theta. Here, theta is in between minus pi less than theta less than or equal to pi. About the origin. The function, here the function fz is equal to 1 by z square. By z square, where of course the z not equal to 0 is continuous everywhere except at the origin and has an antiderivative. Fz is equal to what? It is minus 1 by z. Of course, here also z not equal to 0. In the domain mod z greater than 0, consisting of the entire z plane with the origin deleted. Hence, by the equivalence of statements A and C in theorem 1, integral over C dz by z square is equal to 0. Next example, that is, here we have to evaluate integral over C e raised to pi z dz, where C is any contour from 0 to 1 plus I. Here fz is e raised to pi z, it is continuous everywhere, and since d by dz of e raised to pi z by pi is equal to what? E raised to pi z. Fz has an antiderivative, that is capital Fz is equal to e raised to pi z by pi for every complex number set. Hence, by theorem 1, integral of Fz along C, where C is any contour joining 0 to 1 plus I, depends what? Only on the endpoints. Here it is 0 and 1 plus I, and integral over C e raised to pi z dz. Integral over C e raised to pi z dz can be written as, which is equal to integral over lower limit is 0, upper limit is 1 plus I fz dz. This can be written as what? F of upper limit we have 1 plus I minus f of 0. It is equal to e raised to pi into 1 plus I by pi minus e raised to 0 by pi. On simplification, we get it is 1 by pi into e raised to pi minus 2. Next example. Next example is to evaluate integral over c 1 by z dz, where this c is the right hand half of the circle, mod z is equal to 2, from z is equal to minus 2i to z is equal to plus 2i. That is, it is just like this. This is our 2i, this is our minus 2i. Here our c. Now we have the solution, that is, let D be the domain mod z greater than 0 minus pi less than argument of z less than pi, consisting of the entire complex plane with the origin and the negative real axis excluded. That is, this is our origin, it is excluded, and the negative x axis. This is our x axis and this is our negative x axis, this one. These two are excluded. C is a contour joining minus 2i to 2i. So, this is, here C is just like this, it is from minus 2i to 2i. And it is contained in the domain D. In D, origin is not included and hence f z is equal to 1 by z is continuous. So, no problem with f z. The principal branch log z of the logarithmic function serves as an antiderivative of the continuous function 1 by z throughout D. Hence, we take f z is equal to f z is equal to log z. Then f dash z is equal to small f z, which is equal to 1 by z for all z belongs to D. Hence, by theorem 1, integral of f z along C, where C is any contour joining minus 2i to plus 2i, depends what only on the endpoints. Our endpoints are minus 2i and plus 2i, and hence integral over C 1 by z dz is equal to integral over C 1 by z dz. This can be written as integral over minus 2i to 2i f z dz. That is, since we have 2i is equal to 2 into 0 plus I into 1, which is equal to 2 into e raised to I pi by 2, we have log 2i is equal to ln 2 plus I into pi by 2. Also, since minus 2i is equal to 2 into 0 plus I into minus 1, which is equal to 2 into e raised to minus I pi by 2. So, we have log of log of minus 2i, which is equal to ln 2 minus I into pi by 2. Similarly, we have stated log 2i is equal to ln 2 plus I into pi by 2. So, it is equal to, so altogether it is equal to what? Ln 2 plus I into pi by 2, that is our first term, ln 2 plus I into pi by 2, minus, second one is ln 2 minus I into pi by 2, which is equal to pi I. On simplification, the answer is pi I. Next example is use an antiderivative to evaluate the integral over c z raised to 1 by 2 dz. Integral over c z raised to 1 by 2 dz, where the integrand is the branch integral over c z raised to 1 by 2 is equal to square root of, it is equal to, here I can write, which is equal to square root of r into e raised to I theta by 2. Here r is greater than 0 and theta lies in between 0 and 2 pi, that is 0 less than theta less than 2 pi of the square root function, and c is any contour from z is equal to first one, that is c is any contour from z is equal to minus 3 to z is equal to 3, which except for its endpoints lies above the x-axis. The second one, that is the B one, is c is any contour from z is equal to minus 3 to 3, which except for its endpoints lies below the x-axis. And third one, c is any closed contour in the counterclockwise direction passing through z is equal to minus 3 and z is equal to 3, which except for the points z is equal to minus 3 and z is equal to 3 contains no other points of x-axis. That is, it is just like this. First one, solution. Before moving to solution, we have this figure. This is our minus 3, here it is our x-axis, y-axis, this is our 3. This is our C or the curve. Let our fz is equal to z raised to 1 by 2, or we can write it as root r into e raised to I theta by 2, where this r is greater than 0 and 0 less than theta less than 2 pi. Now, first solution, that is the part A solution. The C is any contour from z is equal to minus 3 to 3, which except for its endpoints lies above the x-axis. Since fz is not defined on the ray theta is equal to 0, that is positive x-axis, fz is not defined at z is equal to 3. At all other points of C, fz is defined and is continuous. Now, consider another branch of z raised to 1 by 2 given by f1 of z is equal to square root of r e raised to I theta by 2, where of course this r is greater than 0 and this theta lies in between minus pi by 2 less than theta less than 3 pi by 2. Clearly, this f1 set is defined and is continuous everywhere on C. Also, values of f1 set at all points on C except at z is equal to 3 coincide with those of our integrand f of z. Hence, in integral over C fz dz, fz can be replaced by our f1 set. An antiderivative of f1 set is the function f1 set is equal to, it is equal to 2 by 3 into z raised to 3 by 2, or which is equal to 2 by 3 into r into square root of r e raised to I 3 theta by 2, where this r greater than 0 and theta lies in between minus pi by 2 and 3 pi by 2. Hence, integral over C z raised to 1 by 2 dz is equal to integral over C fz dz, which is again equal to integral over C z raised to 1 by 2 dz, which is equal to integral over C fz dz, which is again equal to what? Our integral over minus 3 to 3, it is f1 of z dz, that is which is equal to f1 of set. Here it varies from minus 3 to 3, which is equal to 2 into root 3 into e raised to I 0 minus e raised to I into 3 pi by 2. Since at z is equal to 3, r is equal to 3, theta is equal to 0. And at z is equal to minus 3, r is equal to 3, theta is equal to pi. So, it is altogether which is equal to 2 into root 3 into 1 plus I. So, next is C is any contour from, that is the B part. C is any contour from z is equal to minus 3 to z is equal to 3, which except for its endpoints lies below the x axis. So, our figure is just like this. It is again from minus 3 to 3, but it lies below the x axis. Since fz is not defined on the ray theta is equal to 0, fz is not defined at z is equal to 3. At all other points of C, fz is defined and is continuous. Now consider another branch of z raised to 1 by 2 given by f2z is equal to, it is equal to root r e raised to I theta by 2, where r greater than 0, theta varies from r greater than 0, theta varies from pi by 2 less than theta less than 5 pi by 2. Clearly, this f2 set is defined and is continuous everywhere on C. That is, f2 set is not defined on the ray theta is equal to pi by 2. Also, values of f2 set at all points on C except at z is equal to 3 coincide with those of our integrand f set. Hence, in the integral of f set along C, f set can be replaced by our f2 set. An antiderivative of f2 set is the analytic function f1 z is equal to 2 by 3 into z raised to 3 by 2. That is 2 by 3 into z raised to 3 by 2, which is equal to 2 by 3 into r into root r e raised to I 3 theta by 2. Here also r greater than 0 and theta varies in between pi by 2 and 5 pi by 2. Hence, integral over C z raised to 1 by 2 dz which is equal to integral over C f z dz. It is again equal to lower limit is minus 3 up to upper limit 3 f2 z dz, that is equal to f2 z over the limits minus 3 to 3, which is equal to 2 root 3 into e raised to I 3 pi minus e raised to I 3 pi by 2, that is which is equal to e raised to I 3 pi minus e raised to I 3 pi by 2. Since at z is equal to 3, r is equal to 3, theta is equal to 2 pi, and at z is equal to minus 3, r is equal to 3, theta is equal to pi. Therefore, it is equal to 2 root 3 into 1 minus 1 plus I. This is the answer of the second part. Next we have, that is the C part. Here C is a closed contour in the counterclockwise direction passing through z is equal to minus 3 and z is equal to 3, which except for the point z is equal to minus 3 and z is equal to 3 contains no other points of x axis. That is here it is minus 3 and 3. Then C can be written as C is equal to C2 minus C1, where C1 is the contour which is the part of C above the x axis, and which extends from minus 3 to 3. Here we have the C1. Minus C1 is the contour that extends from 3 to minus 3. And C2 is the contour which is a part of C below the x-axis and which extends from minus z is equal to minus 3 to z is equal to 3. That is, here is our C2. From A and B, we have integral over C f z dz is equal to, that is integral over C f z dz, which is equal to 2 root 3 into 1 plus I, and integral over C, here it is integral over C1 and it is integral over C2 f z dz is equal to 2 root 3 into minus 1 plus I. Hence, integral over C z raised to 1 by 2 dz. This is equal to what? Integral over C2 minus C1 f z dz. And we can write this as it is integral over C2 f z dz. It is integral over C2 f z dz minus integral over C1 f z dz. So, by substituting the values here, the final answer is, it is minus 4 root 3. So, here comes our proof. Hope you enjoy the session. See you next time. Till then, take care.